So I'm going to talk about hardness amplification and proof complexity, and I'll try to explain the title. Probably I'll explain all the words of the title. I think many of you probably know more about proof complexity than maybe I assume, so I hope I'm not going to bore you a little too much. Anyway, this is joint work with Tony Patassi from University of Toronto and my student Trin Hun from University of Washington. So, just to review proof complexity, and maybe this isn't quite the standard definition, the original definition of Cook and Reckow, but I'll just use it for convenience because it sort of fits our notion of NP a little more nicely. So I'm going to say a propositional proof system is going to be identified with a polynomial time verification algorithm, such that, and it's going to be a proof of unsatisfiability, so such that for every formula f, the formula is unsatisfiable if and only if there's a string, p, or proof that verifier will accept that proves this formula is unsatisfiable. So if it's unsatisfiable if there's a proof, if it's satisfiable, then there's no proof. And it'll be polynomially bounded if and only if we can add the requirement that the length of the proof is polynomial. So if one exists, it's going to be of polynomial length. So what are some motivations for studying proof complexity, and in particular what we're going to be doing today, which are lower bounds in proof complexity? Well, the big one is the one due to Cook and Reckow, and it's a little more obvious in this phrasing than in their original phrasing, that NP is equal to co-NP if and only if there exists a polynomially bounded propositional proof system. And so in particular, if we could show that there's no polynomially bounded proof system, of course we show NP is different from co-NP, and therefore P is not equal to NP. So that's one reason. Another reason is that lower bounds for specific proof systems, some of the systems that we will discuss today, rule out large classes of algorithms for solving satisfiability. So many satisfiability algorithms, when they fail, end up producing proofs of unsatisfiability. And so if we can lower bound those proof systems, we get lower bounds for algorithms, large class of algorithms solving SAT. And the third motivation, which is actually one of the main motivations for studying some of the specific proof systems we consider, is that many of the best approximation algorithms for NP-hard problems are done using linear programming or semi-definite programming, and those algorithms, the algorithms are based on inferences done using some of the proof systems that we'll discuss, LS plus and CP, which we'll talk about later. And so lower bounds show limitation on these techniques. So even though I describe proof systems in terms of a verifier, what we'll really talk about are going to be what I'll call standard proof systems. So without loss of generality, we're going to assume the formula is in conjunctive normal form, that one can easily make that assumption. So your formula is just a collection of clauses. And in this standard proof system format, a proof of unsatisfiability of f will be a sequence of, and here typically you might say Boolean formulas, but I'm going to think about it as Boolean functions of which we'll call lines that are of some specific form. And it's not going to, I'm not going to specify that exactly in this definition. We'll see some examples. So each line either is one of the input clauses, or it's an axiom, or follows from previous lines. So in other words, it's always true. It's essentially the constant function 1. Or it follows from previous lines via sound inference rule. And not every function, in general, not every function of that evaluates, that is always true would be an axiom. You might have x or not x or something like that would be an axiom, by the way. So, or it follows from previous lines by a sound inference. And here, all we mean is that if fi and fj both evaluate to true under 0, 1 assignments to the variables, then fk will evaluate to true under that assignment. So notice this doesn't say anything syntactic, and at the end we end up with some sort of trivial contradiction, and we'll like x and not x, or even the empty clause. Now, in order to be a proper proof system, these sound inferences must be efficient to check. There would be 2 to the n of these assignments to check in general. So in order to fit into the standard propositional proof system definition, we'd have to have an efficient algorithm to check that this line fk does indeed follow from lines fi and fj. We will also consider, though, a stronger semantic version where we don't have this requirement. Because we're going to be proving lower bounds, we're going to be able to do this. In order for this to make any sense, we're going to have to make use of the properties of the special form of the lines. Because if we allowed any sound line to be inferred, we could infer any tautology we want instantly in one step. So, but we can do this and consider semantic inferences and get something interesting, provided we require that these lines be of some special restricted form.
Isn't there also a condition against blowing up the length of the lines?
We are, again, the form of the lines is not going to be of issue, so I haven't even described the length of a line. We're only going to count the number of lines in proofs or other properties. So for us, and this is actually relates to this question, we can take a proof and view it as a sequence of inferences here from bottom to top, where at the leaves or at the sources we have clauses or possibly axioms. And at each internal node we have some inference rule. And so we label the internal node by one of the lines of the proof. And the last line is this trivial contradiction, which we can think of as the root of this DAG. Size, for us, will be the number of nodes in this. So it's obviously a lower bound because you might have really long lines. So for us, size will be number of nodes, and rank will be the depth of this graph. In general, we won't be able to do size of arbitrarily structured proofs, but we will be able to talk about size of proofs that are tree-like. In other words, that the inferences, this graph of inferences forms a tree. For the purposes of rank, it doesn't matter whether it's a tree or a DAG because we can just expand out nodes. So you can either think of it as rank as applying to a general proof or a tree-like proof. It doesn't matter. So what is an example of a standard proof system? Here's one where there's no issue. Every line is nice and short. So in resolution, you start with your unsatisfiable set of clauses F. So each of those could be a source. Given 2 clauses which contain variables of opposite signs, you can combine them and resolve them and get A or B. And our contradiction clause is the empty clause, and that's derivable if and only if F is unsatisfiable. So pretty much the most trivial proof system. It is extremely simple, and in the tree-like form, it actually is the DPLL algorithm used in practice fits into the tree-like form. So resolution and subclasses are actually used a great deal in practice, but from our point of view, it's a proof system that we understand extremely well and we can analyze very well at this point. Most of what I'm going to talk about today concentrates on polynomial threshold proofs of various sorts. So here, lines are integer polynomial inequalities. So again, so for example, in general, so in order to use these lines, we have to replace our clause by an associated inequality. And here we just do it in kind of the obvious way. A variable goes positively, not a negated variable is 1 minus that variable, and the right-hand side is 1. And here, to do inferences, we add the inequalities xi is bigger than or equal to 0, and 1 minus xi is bigger than or equal to 0 to indicate that these are Boolean, although these are only real. As stated, they apply to all real values. And the goal, the standard contradiction here, is 0 is bigger than or equal to 1. Okay? So there are a number of systems in the literature that fit this polynomial threshold proofs. And I'm going to go through them later, just after this slide. So one is cutting planes, which I'll mostly use CP for, defined by Gomery and Fatal, even for non-Boolean cases for integer programming. And then for 0-1 programming, various forms of systems by Lovász and Scriver, which are denoted by various LS, possibly empty with a plus, with a star, with a plus and a star, and I'll explain that a little bit. Each has specific rules, but every line, every inference in every line is at most quadratic in the case of LS. And one can come up with higher degree proof systems. Some that are known are due to Shirali Adams or Lasserre. One can also very more nicely, quite nicely, make higher degree extensions of these LS rules and of the cutting plane rules. And these, for example, were introduced, as far as I know, in a paper by Grigoriev, Hirsch, and Paseknik. So what are the rules of cutting planes? So the first rule is a rule that would apply for any inequality over the reals. So this is if we have a bunch of inequalities, sum of AI, xi is bigger than or equal to bi, we can take, and we've got a bunch of coefficients, non-negative coefficients, we can take linear combinations of those inequalities in any arbitrary way. Now, that is only ever going to give us the inequalities that apply only apply to the reals as well as to integers. We might be able to get stronger results if we knew that the points are integral. And so this cut rule or cutting rule for the or division rule of cutting planes proof system actually you can think of as slicing inside the rational polytope to get closer to the integral polytope, sliding one of its boundaries. And here, if you've got an inequality, notice the C is a common factor in all these, we can divide it out. And so we get something that's fractional. But we know because the quantities are integral on the left, if it's bigger than B over C, it's bigger than the ceiling of B over C. And so that gives you a stronger inequality. And this is the inequality that allows you to get a complete proof system for propositional formulas and allows it to, you can easily show that it is more efficient, or at least as efficient as resolution, for example. Lovász-Scriver systems have somewhat different rules. They don't have the division rule, and it's some question of whether they can even simulate that efficiently. So here we know that if we can take an inequality, multiply it by a non-negative quantity, it's still valid. Well, xi and 1 minus xi are still valid. So we can multiply a linear inequality by those terms, take positive linear combination as the result, and we obtain a quadratic form. And we can also, so in that quadratic form, let's suppose that if all the cross terms cancel, and we can replace, we can do one other transformation. If we have an xi squared, because our variables are 0, 1 variables, we know xi squared is the same as xi, so we replace that. So you can lift by these multiplications to quadratic inequalities and then project down to the linear portion. So by taking these linear combinations, these positive linear combinations. And so LS inferences are all of this lift and project variety of some sort. You go to a higher degree and you project down. Here you get to multiply linear inequalities by essentially variables and their negations. In LS plus, yeah. Why project intersect? One, well, I mean, I guess technically the what you get when you project is the linear subspace defined by these quadratic inequalities. There's no particular reason not to keep these quadratic ones around. So do you not get the same thing by projecting? I have to think about that. For the purpose, for the purpose of what I'm going to talk about, what I'm going to be doing is, in some sense, contrasting the specific rules here, which are, they're fairly specific, with, in fact, what we'll be looking at is general rules. So I don't think I just want to give a flavor of the kinds of things one does in specific rules. we're going to get our lower bounds are going to apply no matter whether you project it or intersect it. I mean, we're going to apply generally. So in LS plus inference, just to go on, just to give you an idea, so this is its relationship to semi-definite programming is because you can infer for any linear inequality, you can take its square, that's going to give you a quadratic form, and you know that's non-negative because it's a square. And in LS plus star, in addition to all of the above, you can take not just linear inequalities times the variables of the negation, you can take any two linear inequalities, multiply them, because they're non-negative, that'll preserve the properties, and now you derive a new linear equality, which will be quadratic, and you can use it, and you do this project. So again, so that's LS plus star. Basically what happens when one does higher degree proofs, essentially you can multiply arbitrary inequalities you've got before by these xi's, 1 minus xi's, or even other, so depending if you went to the star form, you could just take two, multiply them together, provided the result has degree at most k. So LS plus 2 is the standard one. And you still get to do this xi squared, or now xi squared gets xi allows you to reduce everything down to linear terms.
Why do you have to have like k?
Well, we're going to parameterize our proofs by the degree of things you allow. No, in principle, you don't need to have a k. You could do polynomial inference. There are issues with verification of identities and so on, so that's one of the things. But in principle, there isn't a well, I'll explain. It'll actually be it's a parameter. And we'll see. So what we're going to talk about today is a generalization of these, which are THK proofs. And this was we defined in a paper with Nate Sagerland. And here, lines are arbitrary degree k polynomial inequalities. So I don't care what form they are. They're just arbitrary degree k in multivariate. And all that we require is that essentially the inferences are sound. So there's no syntactic rule. This is a purely semantic rule. If it's the case over all 0, 1 assignments that h is true whenever f and g is true, you can write down h. It's a binary fan-in system, as opposed to possibly larger fan-in from cutting planes and Lova-Scriver. But it can actually simulate all the other polynomial threshold systems here by just a binary fan-in, because you can prove that the degree of fan-in for the Lasserre, so for LS plus and cutting planes is only polynomial in n. So you can just, with a log n depth, you can simulate it pretty nicely. So this is a semantic proof system. It's not so interesting from the point of view of upper bounds, but we can, because of the verification issue. But from the point of view of lower bounds, it's sort of the strongest proof system for degree k polynomials that you could kind of imagine. Well, why couldn't it be a negation of unsatisfiable formula? Because you'd have to express that unsatisfiable formula by a polynomial of degree k at most. So this is really key. You can't allow arbitrary functions or these semantic proof systems just become trivialities. So the key is the representation capability of the lines. So here is kind of, this includes some other proof systems I haven't discussed, and not all of the other proof systems. I needed some space, so AC0 Frege and some of these others disappeared. But here are some proof systems. We've got resolution. These systems here, which I haven't discussed, are algebraic proof systems. I won't discuss them in detail, although I will mention the consequences. And they're red because basically we have lots of lower bounds for these proof systems in red. Frege, an extended Frege, these are the proof systems that for propositional logic you see in elementary textbooks. ZFC is Zermelo, the usual thing. Zermelo-Frankel set theory with the axiom of choice, and there's an arrow above. We don't even know that there's an optimal, most powerful proof system. We've got cutting planes here, and Lova-Scriver LS+, I haven't put all of them, and the TH proof systems that I mentioned. So I put them in a different color because they're not really proof systems in the standard sense, but they're these strong semantic proof systems. So what we'd like to be able to do is, in general, understand these other algebraic proof systems as well as we understand the proof systems here in red. I mean, of course, we'd like to move up to Frege, extended Frege, but that's way beyond our capabilities at this point. Notice Frege doesn't sit above these because of the semantic nature of these proof systems. What we're going to be interested in are rank predominantly and also tree-like size. And I want to give some justification for why rank and tree-like size. So proofs of rank R have n to the order R size tree-like proofs. And often they can be found and in the proof system. It can optimize over inferences of rank R in time n to the order R. So if you have a small rank proof and you can infer some inequality or condition, say, for example, on your objective function for something expressing a 0-1 programming problem in rank R, then you actually have a reasonably efficient algorithm. And that's, in some sense, one of the reasons why these proof systems are very good from the point of view of approximation algorithms. In particular, cutting planes is useful for LP relaxations of NP-hard problems. So again, here's the, you start with a natural 0-1 program, relax to LP, apply small rank cutting planes inference to get a stronger LP, and you can solve that stronger LP to get an approximation to your problem. Essentially, LS plus and degree 2 Lasserre have a similar role with respect to semi-definite programming. You can think of the Gomans-Williamson max cut approximation as an LS plus inference of rank R starting from a natural linear program. Recently, Raghavendra has shown that the unique games conjecture implies that rank 2 Lasserre gives optimal approximation to many constraint satisfaction problems. So this is one of the reasons why proof complexity has been interesting for that under that third bullet, and why rank has been particularly interesting. As a result, there's been a lot of work on rank lower bounds for obtaining approximations, not proofs of unsatisfiability, but saying that your inferred maximum objective function value, for example, is only a certain fraction of the optima after a certain time period. And these are often in very specific proof systems, CP, LS, LS plus. The methods are fairly ad hoc and apply to those proof systems. They apply to problems like vertex cover and max cut and so on, so specific problems. There's another class of actually nice proofs, it's less well known, which give lower bounds for LS plus tree-like size and also rank as a consequence of the previous slide, based on algebraic proof system lower bounds. And these apply to certain specific principles like mod 2 principle and Zeiten tautologies that have been previously studied in the algebraic context. And one thing I should mention is a nice result of Patassi and Segerland that many of these rank lower bounds actually also, if proven in these ad hoc ways, just as rank lower bounds, also apply to tree-like size, which is not an immediate, unobvious consequence, using the same techniques as these papers. Finally, I'd like to mention, although they are for specific proof system, there's some really nice results of Schoenebeck and Tulsiani in the past, little over the past year, that gives very strong specific lower bounds for Lasserre for rank of Lasserre proofs, though not tree-like size, for a number of nice NP-hard problems. So that's really nice work. That's in some sense orthogonal to what I'm going to talk about today. So what I'm going to talk about today is based on a different approach that we introduced in this earlier paper I mentioned, where we introduced the THK proof system. And that is try to find lower bounds that apply to all of these threshold proof systems at once, that don't rely on the specific inference rules of the proof system. Even the lower bounds for Lasserre, which I like so much from the previous slide, only apply to that particular system of inference rules. And the other part is to use, the key idea is to use a relationship between multi-party communication complexity and these THK proofs, where one looks at a search problem for violated clauses, and I'll explain that problem later. And what we showed in that paper is that we could come up with this very specific unsatisfiable family T that's based on Cyton formulas on high-degree expander graphs with a bunch of other properties. So it's one particular family. And we showed that if you could get a lower bound in this multi-party communication complexity model on the k+1 party set disjointness problem, then you would get large tree-like size for THK proofs. So it was just a reduction. It said if you could get this lower bound, which we kind of believed was true but didn't have the proofs for, then you could get the lower bound for the proof complexity. Well, about a year ago, or a little more than a year ago, Lee and Schreibman and Chattopadhyay and Aada actually proved these lower bounds for the set disjointness problem. So in that yields lower bounds for this family of formulas. One drawback, it's just one formula. It's a very specific thing. I don't know who was interested in the particular extended Cyton tautology inherently. But the other thing is the proof is very complex and tedious, lots of details. And if you tried to do this for anything else, it's not clear that that you'd get anything would come of it. So the main results I'm talking about today are that we can get this kind of result in an extremely general way, and it's actually not so hard to follow. So what we can show is a way of taking the hardness of a function family F of CNF formulas. So I've stated this in asymptotic notation. Is the only reason I've used the term family. But just think of a formula F, 3 CNF formula, say it doesn't have to be 3, it can be just small constant, in M variables that requires large resolution rank R. You can take that formula, and for any k that's not too big, you can apply some operation to that formula that lifts it to a new formula G. It's going to depend a lot on the original formula. It's going to have some extra stuff. The size of the new formula is going to be m to the order k. So it goes up by a kth power. The rank of this new formula will be in THK+1 refutation. So you lift k, you get sorry, this should say THK refutations. Actually, it shouldn't be k+1. THK refutations is at least polynomial in R. This should be an omega, not an O, divided by polylog m. So, and the tree-like size is essentially exponential in R. So just to give an idea, so large rank, you can do everything in linear rank. So this says we've got at least polynomial rank. And in fact, many, many large natural classes of formulas are known to require linear resolution rank. So let's say you take a formula of linear resolution rank, you apply this operation, you get something of polynomial rank, like n to the epsilon for some constant epsilon, like a 7th. It'll be, I believe it's a 7th, divided by polylog m. And you'll get size exponential for tree-like proofs in THK refutations. And this works even for k up to double log m, not just constant k. And we have an almost matching upper bound on the rank of the formula. So there are very, you can get proofs of small rank for these formulas. So they're not that complicated formulas. Other results, we can get hierarchy separations. There are natural formulas that have proofs in CPK, so that have cutting planes proof of k, so in a real proof system, but require large rank and exponential tree size even if you try to drop the degree by 1. Okay, essentially the same kinds of lower bounds as we get for the specific formula. Well, this is take the cutting planes rules, and I allow you to multiply by xi provided the product is at most k. We've got the division rule. So we've got the division with rounding rule. We don't know. I don't know the relationship. We don't know whether CP can simulate LS or LS can simulate CP. They're incomparable.
So in LS you can replace x squared by x, and in CP you cannot.
Right.
But in CP you can do rounding, and in LS you can't.
This means that CP operates only with multilinear polynomials.
Yeah. I'm gonna charge you xi squared. I'm gonna charge you 2 for an xi squared. In CP, I would charge you 2 for that xi squared. You can't replace it by xi.
Well, I cannot.
You cannot replace it by xi.
It means that it's multilinear, basically. Multilinear or something like that.
No. It counts towards your degree. You can't reduce it.
The degree can
The low end slider is multilinear,
yes.
Yeah.
but they don't round.
Yeah. Anyway, it happens that it has a nice proof in CPK. I believe it also has a nice proof in LS. The only issue is it might be like LS2K. I mean, it's sort of it's a little less sharp. The degree stuff with LS, because of this lift and project, it gets a little funny because of the way the squares add it. Also, and this is a result as of about a week ago. So suppose you've got some 3CNF formula that rank R resolution can't refute. But that formula is actually very far from satisfiable. Only a 1 minus delta fraction of the clauses can be simultaneously satisfied. Then we can get an integrality gap that's off by a factor of 8. So it's 1 minus delta by 8 for the LP or for a lifted formula. This only applies, though, for TH1 formulas, so generalization of cutting planes. So this kind of result, and it gets polynomial rank lower bound and also exponential tree size, although I don't think we wrote that out. So this is a separate, stronger result that allows us to get integrality gaps in the case of TH1. So how do we actually do this? We actually get the rank and tree-like size lower bounds by looking to an even stronger class of proofs than THK proofs, which we call T. There's a superscript CC for communication complexity of K and R CC of K. These are two proof systems. The T, if you get lower bounds for that, you get tree-like lower bounds. You get lower bounds for R, you get rank lower bounds. The R is actually a stronger proof system. And these apply to all of these proof systems and some others. In particular, by doing it for these proof systems, we get lower bounds as well for all of those algebraic systems. Okay? So, and applies to Shirali-Adams and Lasserre and so on. Okay. So now we've got a hierarchy with some more proof systems in it. So more unrealistic proof systems for which we're going to prove lower bounds. Unrealistically strong proof systems so which we're going to get lower bounds. And we'll see that, in fact, there's a shift by 1, which is from the TH proof systems to the just in our terminology. So I haven't explained what they are, and I'll do. That line is dotted because I can't say that. So the degree here corresponds to the K up there. So I don't know which thing I would put polynomial calculus up to there. So it would be degree K polynomial calculus. No. What I'm saying, so I can't put a line to any specific thing in that picture. So I'm just saying the degree K limited polynomial calculus goes to the K, or a K plus first thing in that hierarchy. So that's why. That's the only reason why it's dotted. It's not clear where it goes. So I didn't want to say it's going to the cloud. So anyway, it covers a lot of ground in this picture. There are some things that I didn't put in the picture, like AC0 Frege, that don't fit in this. But anyway. Okay, so what our result is, I use the title hardness amplification because that's what people understand. It's actually a hardness escalation result in the following sense. A typical hardness amplification result is that if you start with some function f that's weakly hard in some sense, say any circuit in some class C has some at least tiny fraction of error, you create a harder G such that say any circuit in a slightly smaller class is very far from being able to compute it, say has error exponentially close to random guessing. So that's a typical hardness amplification result. We're doing something else. We're taking a function f that is hard for a weak class and creating a g that is nearly as hard, but with respect to a much larger class C prime. So what's happening, it's almost like a dual way of saying I've got a hard function. And the nice term for this is hardness escalation, but if I put that in the title, nobody would know what the heck I was talking about. So we used amplification. We tested, we did a little market research and discovered nobody knew what hardness escalation was and were confused by it. So we decided to keep it out of the title but mentioned in the paper. The inspirations for our hardness escalation results are some monotone circuit lower bounds should be for decision trees, not from decision trees, by Ross and Mackenzie. Oh, no, it is from decision trees. That's right. So you get monotone circuit lower bounds by studying decision trees. And the pattern matrix method in communication complexity. I'm not a super fan of the title, of the terminology, but I'm going to use it. So this is a method introduced by Cherstov in the two-party case, and Leon Schreiber, Chadopadhyay, actually in a separate paper, actually first talked about it, and the results that I mentioned before about disjointness apply using this technique. So what I'm going to do in the remaining few minutes of the talk, 20 minutes or so, I guess, I hope, is talk about an outline of the methods to do it. So one of the things is I've hinted at a relationship between the refutation problem and search problems. The connection between multi-party communication complexity and its connection to search problems. I'm going to review this pattern matrix method, and then our technique is going to be a modification and extension of the ideas of pattern matrix method to proof complexity directly, rather than just using one of the results of it, as was the case for this one example using disjointness. So what is this relationship between refutation and search? So here is a standard resolution refutation, and so I've got the clauses, they're at the leaves, this one happens to be tree-like. The internal nodes are labeled by the clause that's the resolvent, and I've also labeled it by the variable that's resolved on. In the case, the C is the variable resolved on over there, and that labels the left-hand one. This same tree can be viewed as a method of solving a particular search problem associated with this set of clauses. Because this is an unsatisfiable set of clauses, we know on every truth assignment there's going to be some clause that's set to be false under that truth assignment. So the problem F search is going to be to output some clause that's falsified by its input truth assignment. So given a truth assignment, spit out some clause that's false under that assignment. Now here's how we can take this proof tree and make it into an algorithm, a decision tree for this search problem. So we have the label of each node, and there's a resolvent. So this to the which side is going to be falsified. So this side is falsified by 0, is assigning A to 0. This side is falsified by assigning A to 1. So we do a branch on this variable on the assignment. So there's the assignment A goes to 1, B goes to 0, C goes to 0, D goes to 1. So we follow the A goes to 0 side. Then we query B. B has value 0. Then we query D. D has value 1. So we get here, which is clause 5. Okay? So this is how the resolution rank is exactly the height of the decision tree for F search. And if you have such a decision tree, it's easy enough to turn it into a resolution proof, a tree resolution proof. Okay? So that's the thing. So resolution rank equals decision tree height of this search problem. Notice there could be, in general, more than one answer to this search problem. All right. Okay, multi-party communication complexity. So here we have k players. Each has an n-bit input. And the communication is a broadcast communication. Everyone knows everybody else's input but their own. So this is called the number on the forehead model, because you can see what's written on somebody's forehead, or it's used in the hats problem. Lazia has some really nice key early papers on this that are actually underlying some of the results we're going to talk about. And we're going to be interested in both randomized and non-deterministic communication complexity. Mostly our lower bounds are going to be randomized, but we're going to be limited by non-deterministic complexity. So in the randomized case, we have access to shared random bits. So this k-party set disjointness problem, which is a generalization of the two-party case, is given these bit vectors, is there some index I such that xij equals 1 for all I? Really, in the k-party case, this is better thought of as set intersection, because the element in common is j, but if we think of each bit vector representing a set, but set disjointness has become the terminology for the hard problem that's of this type, and so we're going to stick with this terminology. So that's the lower bound, and this is hard for two-party communication complexity and indeed all constant communication complexity. So that's just one example of a problem. We started with resolution rank and the search problem. What about Thk refutation? So again, here we've got our input clauses. Here we have our conditions. Although we don't actually necessarily need these. These would be used if we were doing cutting planes or one of the explicit systems. But we get the input inequalities. We can write them in. And here I've written the inequalities associated with the internal lines. Notice this pair of inequalities, if we add them, we get 2a plus b is at least 1. So semantically, that implies a plus b must be at least 1. But that's not a general. So this is an example of a semantic inference in Thk. You can actually simulate this in cutting planes by using some of these other inequalities. And the main result that we're going to rely on is that if you have a small rank Thk refutation, you get a small k plus 1 player communication protocol for the search problem. So here's the details of it, a little bit longer statement. So it's an explicit polynomial, so small, the rank goes up by k cubed polylog n. So here's the proof sketch, and it gives an idea of the connection. So first of all, if we've got degree k polynomial inequalities over 0, 1 valued variables, there aren't that many different monomials. You don't need that many coefficients based on those monomials. And the other is that you can take a degree k polynomial that has some bound on its coefficient. You can verify it with randomized. So if you got just one inequality, you can verify it by a randomized algorithm which doesn't use too many bits in k plus 1 player protocols. So degree k and k plus 1. And the key property, and there are some other things required to speed it up in the randomized case, though, is that each monomial, because it has k different variables, its values can sit on only the foreheads of k different players at most. So there's got to be some player who can see all the bits. So some player can evaluate each monomial. In fact, and so they can work very efficiently. And that's the connection between the degree bound and the number of players. And then once you can evaluate each node of this search problem, of this proof, we can do just like what we did with the resolution and branch based on the value of a node and go to whichever of its children is false, picking arbitrarily if both are false. And so you start at the root and you just find a falsifying path to the leaf. So that's the basic argument. In fact, what we do in general, rather than talking about proofs that are polynomials, we'll just talk about proofs that have multi-party verifiers. So a line will be in the proof system TCC of k if, as a Boolean function, it can be evaluated by a protocol for k players that's randomized and doesn't use too many bits, polylog n bits. Basically, generally one thinks of polylog n as efficient in the case of communication complexity. So that's an efficient protocol. So our CC is a little stronger, will allow the inferences in this system if and only if there's a protocol that will figure out which of the children to go to. So if you have an assignment that falsifies H, you can tell whether it falsifies F or G. Okay? So that's a requirement for the RCC protocol. So that, in fact, allows you to simulate proofs where lines are clauses, each of whose component is a polynomial inequality. So the resolution of THK proofs. In both cases, you can show that small rank still implies that F search is easy for K+1 player communication complexity. So the other key ingredient is the pattern matrix method. So this is a long line of proof methods. You can even get lower bounds for very simple functions that work up to a large number of players. We're going to use mostly this result of Lee and Schreibman, Padilla, and Ada for multi-party communication complexity, and the integrality gap result is going to rely on the Scherstow result. So the method is as follows, and this is a method just on Boolean functions. We're just going to shift gears to think about Boolean functions. So you start with a Boolean function, and you suppose that it has large epsilon approximate degree, where the epsilon approximate degree means it point-wise approximates the value of the function within epsilon. Then you can take that function and lift that to a new function that is hard for a K+1 player number on the forehead communication. So it takes approximate degree to communication complexity. And here is a sort of pictorial version of it. So suppose it's got epsilon approximate degree at least d. Then we put on these selector functions, which I'm going to denote by psi k for each bit. So they're independent selector functions. So each one of these will have a large number of bits of input. And with a particular selector and a particularly large number of bits, double exponential in k number of bits, then the degree translates into communication complexity, which isn't much smaller, d divided by 2 to the order k. And this allows you to get lower bounds for log n players. So this is actually a beautiful line of work, which we're going to be able to use mostly as a black box. So here is what this tensor selector is. So we can think of the bits associated with x and indeed as a cube of a k-dimensional cube of side L. Each of the other players is, so player 0 gets that. Each of the other players gets one hyperplane in that, a specification of which dimension it's going to be in that direction. So we can take all of these three select together and say, that's the point that we want. You now take the value from x and you pass that on to the top level. This is psi 3. So you can just think of that as indexing into x, where each index is ranges from 1 through L. So that's the tensor selector. So we have this thing, though, a mismatch in the statement that we talked about epsilon approximate degree of Boolean functions. That's pretty far from resolution rank. One thing that gets us a little bit closer is that we can connect approximate degree to decision tree height. So there's a nice lemma due to, well, the original simulation due to Nissan and Szekedy, and then Beals et al. Improved the simulation motivated by quantum computation, which says that if you take any Boolean function, its decision tree height is bounded within a polynomial of its epsilon approximate degree. I've written it 5, 6 because it's minus 1, 1. You can take 1/3 if you do 0, 1. So the corollary of this is that rather than assuming epsilon approximate degree, if we're willing to lose up to a power 1/6 loss, we can assume large decision tree complexity for the function f. Okay, so these lower bounds also apply even if you have good decision tree height. Okay, so now we've gotten a little closer. We've got decision tree height, but I haven't gotten the thing of how do we adapt this pattern matrix method for proof complexity. So here we need a lifted formula. How do we take a formula and do something like this selector process? So let's suppose the variables are E1 through En, And we're going to have two parameters, L, which is going to be the side of the cube, which will actually have to be double exponential in K, but not worry about it, and K. So for each bit, and I've dropped one of the indices just so the indices here, dropped the index on the original bit so the indices here are simpler. We're going to have L to the K bits, x sub J1 through Jk. So each Ji is between 1 and L. And we've got KL selector bits, Yij. And we'll have clauses which essentially say exactly one of, for each I, exactly one of the Yij's is 1. So those are nice clauses, easy to add. And now, whenever we have an occurrence of E or not E in our original formula F, in a clause of our original formula F, we want to say that if xj1 through xjk is selected, which is what this tells you that j1 through jk are the correct positions that are being selected, then we'll plug in x, that particular selected one. If this is selected, then we'll plug in the negation of it. Now, these aren't clauses, so we can't substitute and just drop these into every occurrence. So we actually have to convert these to clausal form, and they're very nice, clausal form. So we can just drop, whenever we see an E, we're going to drop this in, but we have to do it in all possible ways. So for each choice of J1 through Jk in each original clause, we're going to have to make copies for every variable in that clause. So each clause of length t will become L to the K to the power t clauses of length, I forgot to correct this, this should be K plus 1 times t rather than t plus 1 times K. Anyway, so the clauses, we get a lot more clauses, but in our parameters this will only be a polynomial blow up in the number of clauses, and they will be a little longer than before. That's right. This says, so we're going to have, so essentially you can think of each clause being prepended by a part that says if the first variable is selected in this way, if the second variable is selected in this way, if the third variable is selected in this way, then this clause must be true. Then the selected version of that clause must be true. So it actually, if you think about it in terms of the implications, it's just a conjunction of those implications implies the clause. This x value is going to be plugged in for E. Think of, right, so this is representing E. Right, the value E. So this just says, if you've got that value, then plug in this. That's the way to think about it. All right. So that's the formula. So it seems like we're pretty good. We're pretty close to being done. We start with G, which is some small ring THK proof. We know, for example, and I could do this with TCC, but anyway, or RCC, but let's just do it in this context. That says the search problem associated with this, polynomial threshold proof has small k plus 1 player communication complexity protocols. Then pattern matrix method. This means this is a decision tree, get small height decision trees, which means, of course, it's got small resolution rank. So there's one rather nasty problem with this. The pattern matrix method applies to Boolean functions, not search problems. So this nice polynomial relationship of degree doesn't work. It turns out that the fix is not that complicated. So we have to create decision problems associated with the F-search problem. So remember, that's given a clause, and a truth assignment evaluates some falsified clause. So it's natural to define a family of functions, F sub S, such that for every subset of possible clauses. So if it evaluates to 1, there has to be something in S falsified by alpha. If it evaluates to 0, there better be something else that's falsified by alpha. Okay, there exists some clause outside of S that's falsified by alpha. We need these two conditions. Once we have this, then the obvious thing, we apply binary search. We query, for example, the left half of the clauses. If that evaluates to true, then we follow down. We know there's an assignment in that subset, so that's good. if it evaluates to 0, if that function evaluates to 0, we know there's a clause outside. So you would think, well, query, what would the answer on the other half? It's possible with this condition that the answer on the two halves are both, it's over in the other half. And so you actually have to come up with a way of coming up with consistent answers. And one way to do it is to say that this family of functions is consistent if for every assignment, if you look at the answers that this function gives on that assignment, it corresponds to, it's consistent with a single falsified clause. So on that assignment, there's some single falsified clause. All sets that contain it answer 1, all sets that don't contain it answer 0. So the nice thing is that if you can show that if it's got a small rank proof, THK proof, then you can come up with a consistent family of randomized protocols. And here you actually have to come up with, it's important that it be consistent even over choices of random assignments, which is not necessarily the typical way you think of answers to randomize answers to search problems or relations. And then it's based on the what I described on the previous slide, this binary search. Given a consistent family, each of which has small height decision trees, then you can get small height decision trees for the search problem, again, by doing that binary search. So the final version of the lower bound is you start with this small rank THK proof. You get a consistent family of solutions G sub S for that K plus 1 player, and these are Boolean functions. Then apply the pattern matrix method to each of those, which gives you small height decision trees. Now, once you've got small height decision trees for these F sub S's, the second lemma, which says we can get small height proofs, small height search trees, which gives us small resolution rank. So if you've got large resolution rank, you can run it up and get large THK proofs, running things in the opposite direction. So there's some parameters. You lose an exponential in K and a power of 6, and a log M for this last simulation of decision trees. And that basically, inverting that gives you the lower bound. I'm nearly done because I realize I'm... so we can get integrality gaps for TH1. Here the key thing is there's a stronger version of this pattern matrix method where you need only 2 bits to select from and 1 bit. So this isn't the case of K equals 1, so we've got just X and Y. So we've got 2 bits for each variable and 1 Y bit to select between them. You only add a single extra variable for each original variable, so you double the length of the clauses. And for example, in 3CNF, there are only 8 clauses in the final formula for the original one, which is why the integrality gaps get preserved except for this factor of 8. So in summary, we've got this general method to translate rank lower bounds, and basically the weakest proof system that people discuss to rank and tree-like size lower bounds for some of the strongest proof systems analyzed. And it's really an extension of the pattern matrix method to proof complexity. Some open problems. It would be really nice to improve this degree K allowed. So we have some results that take this pattern matrix method and allow you to get log-in party communication complexity instead of log-log-n for some pretty simple functions. The problem is they use epsilon alpha approximate degree, a funny notion of degree for which there's no natural decision tree analog, and so we don't have this nice connection. It'd be nice to get better integrality gaps, get integrality gaps for THK for K bigger than 1. And the problem is, once we got K bigger than 1, we're adding polynomial many clauses. Integrality gaps essentially don't translate well under that context, because it's easy to satisfy all but one of the original clauses associated, the new clauses associated with a single original clause. And it'd be nice to know if we can get general size lower bounds using hardness escalation, and maybe start with resolution width rather than rank. In particular, in pure size, we have this nasty thing. We have exactly one example that's hard for cutting planes, really, in terms of size. And that's the only size lower bound known for basically any of these proof systems for general proof size. So